Hello students, welcome back to a new video. In this video, we will try to understand and learn about resistance, resistors and resistivity. So let's begin. The resistance is the property of a conductor to resist the flow of charges through it. Because as we know, current is nothing but the flow of charges. So when we connect a resistor in a circuit, suppose the resistance is R, then the flow of current will depend on the voltage and the resistance connected in the circuit. Now you might be wondering, where did this come from? So let's see. Let us talk about the Ohm's law. Now according to the Ohm's law, the amount of electric current is directly proportional to the voltage of the circuit or connected in the circuit. Suppose we have a circuit with resistance R and voltage, the battery V, then according to Ohm's law, V is directly proportional to I, where I is the current. So when we will remove the proportionality sign, we used to put a constant. So in this case, the constant will be R. So we have a formula V is equals to IR from the Ohm's law. We can derive other formulas from this formula, like I is equals to V upon R, or R is equals to V upon I. So now as we know about the Ohm's law, let's try to understand the relationship between V and I graphically. Now suppose we have voltage on the y-axis and current on the x-axis, then since V is directly proportional to I, so there will be a straight line which will represent the relationship between V and I. At any point, we can calculate the value of R as V upon I, because at the y-axis there will be some value of the voltage and some value of the current. So at this point, the resistance can be calculated as V1 by I1. So if the value of resistance is R, then the voltage in the circuit will be V1 and the current in the circuit will be I1. So there will be a straight line which represents the graphical relationship between voltage and the current. Let's talk about resistors. Let's understand what resistors are. Resistors are the components that are used in an electric circuit to cause resistance to the flow of current. A resistor in an electric circuit usually looks like this, represented by R. The resistance is represented by R for this resistor. So it can be any material. If there's a conductor, the resistance will be comparatively low. And if it's an insulator, the resistance will be comparatively high. So now that we know about resistors and resistance, we will try to understand that on what factors the value of R depends. Very first thing is the length of the wire or the conductor or material for that matter, represented by L. The second thing is the area of cross section, represented by A. Now let's see what's the area of cross section and the length in case of a wire looks like. Suppose we have a piece of wire and we have magnified that piece. It will look something like this. Now this portion is the area of cross section and this is the length of the wire. Now how will the R depend on these factors? R depends directly on the length of the wire and inversely on the area of cross section. So if we combine the both, we get this. So we can say R depends directly on the length of the wire and inversely on the area of cross section. If we combine and try to remove the proportionality sign, then we have to use a constant, which in this case will be rho. Now what is rho? This is the resistivity. Now the resistivity varies from material to material, and the SI unit, if we see that we have R is equals to rho L by A. If we shuffle the variables, then we will get, so we can figure out, since rho is RA by L, then we have the SI unit of R as ohm, area as meter square, and the length as meter. So the end SI unit that we'll get will be rho meter. So the SI unit will be rho meter. Now, as we can see, the resistivity is a constant. So the value for each material will be a constant value on which the resistance will depend. So the resistivity is a property characteristic of a material and will vary from material to material. Suppose we have one conductor, silver, which has the resistivity of 1.6 into 10 to the power minus 8 rho meter. We have another alloy, constantan. It has a resistivity 10 to the power minus 6 meter. And suppose we have an insulator, glass. It has a resistivity of 10 to the power 14 to the 10 to the power 18 meter. See, in case of a conductor, the resistivity is very low as compared to both insulators and alloys. And in case of constantan, which is an alloy, resistivity is low as compared to glass or an insulator and is high as compared to the conductor. Now in the case of an insulator, the resistivity is very high as compared to both a conductor and an alloy. So we can conclude from this that since R is equals to rho L by A. So we can say the conductors have a low resistance. Alloys have moderate value of R, and insulators high value of R. So we can conclude the lower the value of rho, the better the conductor. Now that we know about all three resistance, resistors, and resistivity, now we will see in how many types or in how many ways the resistors can be connected in a circuit. The first type that we have is series. Now suppose we have three resistors R1, R2 and R3 connected in a circuit in series. It will look like this, connected to a battery of some voltage. Closed switch can be there. So this is how circuit will look like for series network or resistors connected in a series. So the equivalent resistance, that is the effective resistance in this circuit, will be calculated by simply adding up the resistances in this case. In a series combination, the current is same across all the resistance. Now let us understand the second way, that is in a parallel system. It will look like this, connected to a battery of certain voltage with a closed switch. Suppose the resistances are R1, R2 and R3 respectively. So in this case, the effective resistance or the equivalent resistance will be calculated in a different way. Like we will start adding up the reciprocals of all the given resistances in a parallel combination. This is how we will calculate the resistance in the given circuit. So as we started in series, the current is same across all the resistors. In this case, in parallel, the voltage across the resistors will remain the same. Now, since we know about series and parallel combinations, we will talk a bit about the ammeter and the voltmeter. So, as the name suggests, the ammeter is used to measure the current in a given circuit, whereas the voltmeter is used to measure the voltage in a circuit. The ammeter looks like this in a circuit, and a voltmeter looks like this in a circuit. But the difference in the two is how they are connected in a circuit. The voltmeter is always connected in parallel, whereas the ammeter is always connected in a series. The ammeter is connected like this, whereas a voltmeter is connected like this. So here you can see the ammeter is connected in series and the voltmeter is connected in parallel. As we know that the current in series remains the same across all the resistors or appliances for that matter. The resistance in an ammeter is very low, whereas in voltmeter, since the voltage remains same across all the appliances, the resistance is very high. The resistance is negligible in an ammeter, or is very close to zero, whereas the voltmeter has a very high resistance since it has to calculate the voltage in the circuit. So there is a minimum amount or negligible amount of current passing through it, and the same amount of voltage is crossing through it. Let's understand these individually. In case of an ammeter, suppose we have a circuit in which we have two resistors and an ammeter connected to the circuit with a voltage V, a closed switch. So there will be some current passing through it. We know that according to Ohm's law, we have V is equals to IR, and in this case, the equivalent resistance will be calculated like this. So the value of I will depend on the voltage and the equivalent resistance. Here we have assumed that R3 is the resistance of the ammeter. So it's clearly visible that if the value of R3 is high, then the value of I will have a decline, and we don't want that. So R3, or the value of resistance of the ammeter, will be very close to zero, so that there is no impact of ammeter on the overall current in the circuit. No impact or negligible impact on the overall current, which solves our purpose of measuring the current without affecting the overall current value in the circuit. Now let's see what happens in the case of a voltmeter. In a voltmeter, suppose we have a combination which looks like this, in which voltmeter is connected in parallel combination. It is connected to a voltage V, a battery V, and a closed switch K. So there will be a flow of current through this. Suppose we have the resistances as R1, R2. For this, the equivalent resistance will be plus 1 upon RB, which is the voltmeter's resistance. So, if there is a low resistance associated to the voltmeter, then there will be some amount of electric current passing through it, which we don't want, because we don't want to affect the remaining circuit. We don't want to disrupt the flow of current through the remaining resistors. So there is a high resistance associated to voltmeter, so that no current or negligible current is passing through it, because the purpose of a voltmeter, the use of a voltmeter, is to measure the voltage across the circuit, which it can easily do without affecting the current supply to other resistors, as the voltage in parallel is same. That means whatever amount of voltage is passing through R1 and R2, the same amount of voltage will pass through the V, the voltmeter, without affecting the supply of current in the remaining resistors, that is R1 and R2. So that is all for this video. In the next video, we will try to do a numerical using these concepts. Thanks for watching.